All right, so chapter 6 discusses all about the term work. And to do work, you need energy. So that's a topic that we move into. So when you have to do work, you need energy. And having energy means ability to do work also. So it's kind of works both ways. Okay, if you have work, if you have energy, you can do work, and if you do work, you kind of get energy back. So it's going back and forth. And to do all this work and energy, you need the power of Trinity. Power. So we will be talking about power towards the end. So work, energy, and power. These are the three things involved in this particular chapter. And let's see how you put these things together and understand the real sense, real meaning of these terms. So let's start with the work. Now, work has two kinds of meanings. One is a scientific meaning, which is what we are concerned about, and the other one is a colloquial sort of usage. I've got a lot of work to do, sort of thing. So I'm preparing for a journey, I have a lot of work to do. That work is not really the work we are talking about. We are talking about work as a measured quantity. You should be able to measure that quantity, and it should have definite units for it. And so it is something that you can measure and work with it numerically. And then automatically energy is also something that needs to be measured. So energy can be measured. So these are the things that we're going to do for the time being. Let's start with work. Scientifically. Write down the definition of work. And then after that, we will learn more about it. Write down. Work is said to be done by a force. Work is said to be done by a force. If the force displaces an object, now, pause for a moment and look here for a little demo. Look at the book. I'm having the book right here, and I'm going to apply a force on it, and you watch. Did I apply a force on it right now? Yeah. What force am I applying? What force? Tell me something about that force. If I ask you, tell me the numerical value of that force, can you find it out? Like what? Mass of the book, yeah, I'll tell you the mass of the book. What else? What else do you need? Gravitational acceleration due to gravity. So what is the force? My question is, what's the force? What's the force I'm applying right now on the book? It's weight. It's weight. Simple answer. That's what I wanted. I don't want numbers. I just want you to tell me, what is the force? Kurt, name the force. Basically, it is a weight. What weight is acting downwards, but I'm applying a force upward, which is exactly the same as the weight. Is that okay? Clear? Which way? Which direction I'm applying the force? Up. Now watch what is happening to the book. And I put it there. Did I apply force? Yes. Did I displace it? Yes. Did I do work on the book? Yes. Now, if you say that I did work on the book must have gained something out of my exercise. What energy does the book have here more than what it had here? What energy? Because if you do some work, it is going directly to energy. And you saw that I applied a force, you saw that I moved it, and the book right now sitting there. And my question was, did I do work? You said yes. If I did work on the book must have gained something, correct? So if the book has gained something, tell me what is it gain? What energy did it gain? At least use the names of energy forms that you already know. And then again. Jack McCover, and then Jackson Clark. All right. The heck. Is it GSP thing?
No.
Okay. All right. So, you know the different forms of energy. You know, so far in your middle schools, you have come across some energy forms. All right. Tell me now, what energy does this book have over here more than what it had over here? That's my question. Just give out some answer. Kinetic. If you think of kinetic, you know, kinetic energy is something to do with motion. Is the book moving?
No.
So there's no change of kinetic energy. It's the same at the same level. So even that term does not work. Nothing. I did not do work on the book. Because the book did not gain energy. That's how you look at it. If there is no benefit of your actions, how can you say you did something? Okay? So work done is always referred to an object. Work done on the book. Now, did I do work on my muscles? Yeah, of course I must have, because I carried something and I moved it there. So I did some work. But did anything go into the book? All my exercise, did it go into the book? Nothing. Now watch the second exercise. Second thing. Watch this again. The book, once again. I'm pushing it from here. I pushed it, and the book is now sitting here. Did I do work now? Did I apply force?
Yes.
Did I move the book?
Yes.
Did I do work?
Yes. No.
This time the answer is yes, I did work. Now tell me, what form of energy does this book have over here more than that here? Heat. At the bottom over here, it should be warmer because of friction. And I was working against friction. And that is the energy form that's coming through. Make sense?
Yeah.
So what's the difference between the first exercise and the second exercise? What's basic difference?
You and 1 step on the paper, 1 picked up.
Yeah, in other words, which way did I apply the force in the first one? Which way did I move it? Sideways. And the second one, I pushed it that way and I moved it the same way. So complete that definition. Work is said to be done by force when the force displaces an object in the direction of the force. Complete that. In the direction of the force. In the direction of the force. So if you're actually doing some work, then the force needs to be in the direction of the force. So you already wrote down the definition. Now if this is an object sitting somewhere, if I apply a force that way, and if I displace an object that way, I am doing work on it. And the work done by me depends on two factors, namely the force and the displacement. Because the further I push it, the more I will have to spend, right? The more force I apply, the more I have to do work. So work done is typically the product of the force and the displacement. It is the product of force and displacement. Now, you know that force is a vector quantity and displacement is a vector quantity. But the product of these two vector quantities is a scalar quantity. Scalar here, vector here, and vector here. So the product of two vector quantities can sometimes become a vector and sometimes become a scalar. There are two kinds of multiplications which you will learn later on in math. There are two kinds of vector multiplications. One is called a dot product, which is this, and the other one is called a cross product, which is basically both multiplying. But when you multiply it with the dot product, you end up getting a scalar as the answer. When you multiply something with a cross product, you end up getting a vector as the answer. This is not the case. There are some other cases in physics that you will be reminded of the cross product. The end result will also be a vector. Okay? Now, AP Physics 2, there are some cases where we do that. Okay, so vector multiplied, you're getting a scalar. Work is a scalar quantity. Work has no sense of direction. Work has no sense of direction. It is just energy. So, work is done by F and D. So, when can no work be done? Tell me an example, like some examples of when can no work be done?
You don't apply a force.
You don't apply a force. Like I'm standing next to the table and I'm not applying any force on the table. So, of course, I'm not doing any work. And the other one?
When you apply a force but displace the object in another direction.
We'll get to that one. Yes.
When there's no displacement.
When there's no displacement. Like, look, I'm applying a force on the table. The table didn't move. What work did I do on the table? Nothing. Get it? So, if F is 0, then no work. If D is 0, then no work. So both are equally important. So you need force and displacement to get something done. Now this is the second situation where you apply a force that way and you displace the object that way, just as I did here. I demonstrated that. Right? If you apply a force upward and displace the object this way, no work is done on the object. Work done is 0. When the force is applied in this direction, and if the object moves in that direction or is moving in that direction, when a force is applied in this direction and the object's displacement is in that direction, is it possible? Is this possible? Tell me an example.
Like if you have a hula hoop, you go like, and it comes back to you.
It comes back to you, that's because of gravity, that's normal. Yeah.
It's like wind, stuff like if you there's something behind you.
In other words, air resistance. You're walking this way and the air resistance is applying a force on you backwards. Or you apply brakes of your car. You're driving in that direction, you apply brakes of your car and you're coming to a halt. So this work is negative work. You're taking off the energy of the object because you're doing a negative work. What's my main purpose of coming to this classroom and standing in front of you? To teach physics. So when you come into the room, you come with some knowledge and go out of the room with more knowledge. That is supposed to be the case every day. If that is not happening, that means I'm not doing my work. All right? And to do my work, I need calories. I have to burn that up from my own chemical energy and stuff like that. So if I'm doing something, I'm using my energy to do it, but there must be a gaining aspect as well. So when you walk out of the room, you should go with extra knowledge, which means I've done my work. Is that okay, Michael? Do you get it? That is positive work. I'm doing positive work on you, which means you are gaining. That is positive work. Now this, the force is upward and moving sideways. It's like I'm standing in front of you one day and you come in, and then after that I start saying, all right, pay attention. And I start scribbling on the board, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F, G, H. I just draw lines, squiggles. I just keep working so hard. I'm sweating it out. And finally, the bell rings after 1 hour, 15 minutes. And I'm saying, all right, I'm tired. You're walking out of the room. Do you go out with any extra knowledge?
Yes.
Other than the fact that I'm crazy? All right?
I mean,
You should be just literally walking back out of the room with the same knowledge you came in. That means I did not do a single work on you. And that's because the line of teaching basically was not in the required direction. It was totally off topic. It's like me telling some stories. Okay. It's totally off topic. And therefore, you gain nothing out of this. Now, let's say you come in and I teach you some trigonometric operations or some new Pythagorean theorem and stuff, all rubbish. Imagine I teach you all wrong stuff. I'm confusing you, like you came in with some knowledge and I'm confusing you more than anything else. And then when you leave, like how do you factorize something? You already know how to factorize it. You're doing it successfully in ACTs and all that. But suppose I'm telling you, you do it like this, you do like this and all wrong. Okay? Imagine whatever I teach is completely wrong. It's like erasing the stuff from your brain. And when you walk out, you're like, I think I lost something. Really. That's like negative work. Okay? Just giving an example so that something will stick on your head. So work done, if it is negative, you are killing the energy. The car, when you apply a braking force, the car is going to lose whatever energy it had, and it comes to a halt. Is that clear? Now let's do something which you don't like. You don't like angles, right? So let's say you're applying a force. Let's say you're applying a force. Pay attention. When you have a force at an angle and you're dragging something sideways like that, and if you're pulling it at an angle theta, and the object is getting displaced like that. If the object is getting displaced that way, you know what to do first. When you have force at an angle, what do? Resolve it. Yep, you resolve the force. And what component is this? F what? F cosine, because it's adjacent of angle. And this one is F sine. Now, out of these two components, how much is work done by this? 0, because it's perpendicular. And this is the only component which is doing the work. So the work done in this case is F cosine theta times D, which is what normally we write as F D cosine theta. What we write as F D cosine theta is a general equation. So in terms of work, that's the only equation you're going to bump into. Simple. If theta is 0, that means the force is this way. What is cosine? 0.
1.
And therefore the work done will be FD. Cosine 0 is 1. What if theta is 180? 180 means this one is not here, but here. Yeah, cosine of 180 is -1, so it will be minus FD. And what if theta is 90? Theta is 90. Cosine 90 is 0. And so the work done is 0. In short, if the angle theta is acute angle, then it's a positive work done. If the angle theta is obtuse, which is more than 90 degrees, you're doing negative work. You get it? If it is the right angle, then no work. Any questions on work done? Now, one more little thing is what's a unit of work? Okay. Work done basically is FD. F is newtons and displacement is meters. And Newton meter is a unit of work. And this Newton meter is what is symbolized or shortened as joule. So a Newton meter is a joule. So if you push something with 1 Newton and move it by a displacement of 1 meter, you have done 1 joule of work. Make sense? If I'm pushing this book with 1 Newton force, and I push it for 1 meter, which is that much, you're doing a work of 1 joule. And if you want to break this 1 joule into basic component, basic terms, you can break Newton up. You know what is Newton, right? Mass times acceleration. So mass times acceleration times meter, that is joule. So it actually is kilogram meter square per second square. So 1 joule is basically all this in basic terms. So what is a derived unit of work? Joule or Newton meter, both are okay. Preferably joule. But what are the SI base units of work? That one. This is the base units of work. In other words, joule split into what exactly it's made up of. Okay? Clear? Now let's come to the next term, which is work is over. The work part of it is over. Now how you use this into problem solving and all those things is what we have to look at next. Let's go to the energy concept. Energy. Energy is the ability to do work. You can write there next to it. Ability to do work. If something is capable of using its energy, then that is called ability. Being able to do something. Like, I pushed the book from here to there. I could do it because I had the ability to do it. A dead man is not going to do that. Right? So ability to do work, that's called energy. Energy is kind of classified in different forms. Mainly, main forms of energy are kinetic and then potential. Kinetic energy and potential, these are the main 2 forms of energy. Sometimes we combine them and say mechanical energy. In fact, everything is connected. So anything moving parts, they're all mechanical energies. But that may include some potential as well. So kinetic energy is energy due to motion. Energy due to motion. So if anything is moving, that is kinetic energy. And we'll get there. If anything is moving, it is kinetic energy. Potential energy is energy due to position. Energy due to position is called potential energy. Does this book have potential energy?
Yeah.
How do you know? It is? Is it capable of doing work?
Yeah.
Like what?
Fall off table.
Say it again.
Fall off table.
Fall off the table? Yep. So if it falls off the table, that means it's using its potential energy and then converting it to other forms of energy. In that manner, even a dead man has potential energy. Right? Throw him off a building and he'll land on a car and dent the car. So he can do work with his energy. Now I'm just, don't go thinking about it yet.
Considering that as long as nothing really truly escapes the force of gravity, does that mean everything in the universe has potential energy?
That's true. That is true. Potential energy, everything has, we have enormous amounts of potential energy right now. We have a lot of potential energy. All right, so let's go into the potential. So what is potential? The word potential is something that I use pretty frequently when I do parent-teacher conferences. With parent-teacher conferences, I use the term very much. Because potential means what? It is a capacity to do the work, or ability to, or in a position to do the work. So imagine a parent is coming and sitting in front of me, and I know that the son is going to fail. And if I strike the conversation by saying the first line, your son is going to fail. Okay? Just imagine the situation of the parent. Your son is going to fail. Immediately the parent kind of goes down, all the way down. Even opinion about me also goes down. Everything goes down. And it's kind of desperate because it is not what the parent wanted to hear. Okay? And then later on, if I say, but he's a very pleasant student, he's good, and he's very honest, and he's just doesn't. All the stuff that I mentioned after that is of no good, because initially the first line itself put him down here, and I'm trying to build up some kind of goodness in that boy. Nothing is happening. That is a bad approach. And instead, how should we approach? How will I normally approach? When I know the son is going to fail, I start off by saying, your son has great potentials. Now, what does that simply mean? Nothing. Your son is occupying a seat in this classroom, which means he is capable of doing just like everybody else. That's what it means. Somebody on the street is not in a capacity to learn this material the way you are learning right now. Correct? So, ability to do work, ability to learn something, and all that is for everybody. Cross-country people, they're running, they're getting things accomplished. Yeah? So they did something, they put their hard work. Is it that only he can run and nobody else can? Everyone can run. Everyone can run. But the thing is, we kind of move things aside. Some of us say, oh, I'm too lazy to run. That devotion and that thing is not there. Cross-country students have that. I've seen one thing generally among cross-country students, they are good in studies too. Because they are more organized, I suppose. They have to spend a lot of time outside class and they are more organized and so on. That is what I've noticed so far in the cross-country students whom I've taught. Okay? Anyway. Exceptions can be there possibly, but I'm just generalizing. So potential means ability or capacity. So I start off by saying the good thing, and the parent is so pleased, and he's right there, almost reaching the sky. And then after that I say, he's good in, he's paying attention in class and all that, but he doesn't do his homework on time. And that's why his grades are, and sometimes his homework is totally missed. So he is losing points on that. And because he's not doing the homework assignments regularly, now slowly I'm putting it regularly, his tests are also equally affected. He's not able to really understand the material. And if it goes in this manner, he's ultimately going to fail. Well, I said the same thing now, but that was the last statement compared to the first statement. Right? I put him right there, and I exposed him to the real facts. Then finally I'm saying he is going to fail. That's my final ending statement. Parent is very happy with that approach, shakes hand and goes very confidently, at least the first line stuck with him. My son has great potentials. Everybody has potentials. Only thing is you have to use it. If you just have potentials, but then if you just don't use it properly, that's what I'm saying. Everyone is in the same boat. Everyone should be able to learn exactly like everybody else. What is happening over here is that you're not fully utilizing your capacity to the fullest. And then what happens is grades will start sliding back and forth. So being organized and being, doing stuff well, or at least the best way you can do, then no regrets. Each person has, limitations, I know that. But there is always a best way you can do, the maximum you can do. Put that out. And then later on, don't think about it and say, I could have done better in my class had I organized myself, Some students, learn all these things only when they go to universities. And then they say, what was I doing in high school? I think I should have put more effort into my studies. Too late. Anyway, you still have half of this year next year, so you should be able to do better. Potential energy comes in different forms of potential energy. So what are the different forms of potential energies you can think about? You can have gravitational. You can have gravitational potential energy, commonly known as GPE. Which is energy when you do work against gravitational forces. Like this book. If I'm lifting this book from here, am I applying a force?
Yeah.
And am I displacing it?
Yes.
Am I doing work? And the work that I did is stored in potential energy, gravitational potential energy. How do you know that this thing has potential energy? Release it, and it's coming down, losing that potential energy, and converting it to vibrations and sound and all the type of energies that you heard. Everything came from my calories. Yeah.
So do you instantly regain that potential energy on the moment of impact?
I'm losing. The book is
If
gaining.
you drop the book, would it immediately regain the potential energy it lost from the fall on impact?
I gain?
No, when you drop the book,
Yes.
it loses potential energy as it's falling.
Yes.
Would it immediately regain that potential energy as soon as it impacts the ground?
Not necessarily impacts. As soon as it goes from here, it is converting itself to kinetic energy, and maximum kinetic energy just before impact is maximum. Let's say I give 100 joules here. Just before impact, it will be 100 joules of kinetic energy just by motion. But when it comes to a halt, kinetic energy is completely gone. But that energy is used to shake up all these atoms and molecules on the table, which is what causes vibration on the table, and vibration causes sound. And you heard sound. And maybe a little bit of heat here. All those things. Right? So if someone actually slaps you, the kinetic energy of the hand is landing on your cheek, and it comes abruptly to halt. That means all the kinetic energy of that hand must have gone onto your face, and it causes all the damage. Right? The heat will be pretty warm after one slap. The body temperature over here will be higher than on the other side. Anyway, so kinetic energy can be transferred. That's the very last thing that we're going to talk about in this chapter, which is how energy is going to move from one form to the other form. All right. Gravitational potential energy is energy due to position. Everyone and everything on the Earth's surface and beyond, they all have potential energy. Satellites have potential energies. We have potential. Anything has got potential energy. That's gravitational. Elastic potential energy. Elastic potential energy, or sometimes called strain potential energy, is the energy gained when you try to change the shape of an object. In other words, stretch the molecules from their original positions, like in a spring. When you try to stretch a spring, you're doing work. If I stretch a spring like that, I'm doing work. The energy is stored here as elastic potential energy. Get it? So when I release it, it goes back. So springs, they store elastic potential energy. So anywhere you see a compression sort of thing that is doing the work, anything, it's not really springs. If I take a ruler and if I bend it, it's got, if I bend a ruler, I'm giving it potential energy, elastic potential energy. When I release it, it springs back up. So it gains, regains, or transfers its energy to something else. Bow and arrow. When you pull the bow, you are actually storing energy in the form of elastic potential energy. When you release it, it is transferring that energy to the arrow in the form of kinetic energy. Is that clear? And then we have other forms of energy, electric potential energy. We have magnetic potential energy. So whatever force you can actually think about, you can have potential energies in relation to that. So what is electric potential energy? If I take this a positively charged object, if I take this positively charged object and just move it closer, do I have to do work?
Yeah.
Yes, because there's a force of repulsion. So when I keep it next to it, I have done a lot of work, and what is stored over here is electric potential energy. How do you know it's got electric potential energy? Release this, and you'll see how it goes away, right? Magnetic, same thing. If I have a north pole here, another north here, try to push one into the other, you will have to face the opposition. So you're doing work. And when you do work, it is getting stored in the form of magnetic potential energy, so it can release that energy. So combined, you can say electromagnetic energy. Electromagnetic energy. In fact, the signals that you're receiving on your cell phones, on your antenna, and all those things are electromagnetic energies. They are waves. Electromagnetic signals. Okay, so EM. All right, so now where is heat coming in here? Heat energy.
Friction.
Yeah, so what exactly is heat? Heat is a combination of kinetic and potential energies. If I hit the table like that, the particles of the table will vibrate. And when it vibrates, there is a transfer of kinetic potential between the atoms and molecules. That's basically how it's heat. So in this room, if the temperature goes up, the atoms and molecules are going to go faster. So kinetic energy is connected directly there. Now, there are other forms of energy, like light energy. Light energy is also an electromagnetic form of energy. Right? Light is an electromagnetic form of energy. Chemical energy is of potential energy format. Chemical energy is almost electric potential energy, because when you mix one liquid to the other liquid and they react and they form a new compound, the new compound formed will have bonds newly formed, right? And when there are bonds, there are forces between the molecules and all that. And in some cases, the energy is released, exothermic. In some cases, it needs energy to form those bonds, so it pulls out energy, pulls in energy. And those are kind of chemical reactions. So chemical reactions also will be talking about this. So energy in general. Frictional force, yes, causes heat. So I can just rub my hands like that and cause heat right now. See? Hot. Where did that heat come from?
Yourself.
Myself. My calories burnt. So best way to burn calories, do this, touch on a cold object, transfer all the heat, do this once again, transfer it. You sit in one place and do it, you can lose your calories. Yeah, to lose calories, all you have to do is lose your energy in some form or the other. Or, when it is very cold outside, below zero, go ahead, take a chair, put it down there, sit there bare body. what will happen then? Energy is running out of your body. The body heat, your body heat is running out of your body. And now when the body temperature goes down, your body automatically tries to, maintain your body temperature, because the body temperature needs to be somewhere 98 and so on. So the body will work so hard to keep up the temperature, and therefore it takes your own calories to do the work. Make sense? It takes your calories and does the work. But I'm not asking you to do these extreme things, because when you do something extreme like this, people say you catch cold. Like, okay, you catch cold. Well, there's no such thing as catching cold. You already have the cold.
Is that the whole old cold thing? Is that where Rocky trains in a meat locker?
That's so now the losing calories. Yeah, I mean, if you're exposing to such terrible conditions, you will lose energy, but it is going to take energy from your body, and your body is going to be weak, and that's one of the reasons why you get sick. Now, you're getting sick is not because you caught some new bacteria from outside. It is just because your body became weak, because its focus is basically on temperature and not fighting the bacteria. It's like saying, are there terrorists in this country now?
Yes.
Yes, but they're not active. Why they're not active? Because they're put under check. Because whoever it is who has entered, maybe they are in universities, but people are monitoring them as to what their activities are. Are they just students, or is there any other activity going on? There are people who are following them. So they're kept under check. If there is some unusual activity that's going on, then immediately they know that there's something wrong. They'll be arrested, they'll be questioned, and so on. Now, all that is fine. All those people are there, and they're put under check. What if US faces a very major calamity, natural or whatever, or border, and there's a big problem going on? And when the problem goes on, all the fighting forces, all our forces, instead of focusing on these terrorists sitting here, they'll be all doing their work on the borderline, trying to defend. And what will happen to these terrorists at that time? They're let loose. Nobody's watching them. So they can do whatever nonsense they want. And then they'll create a big mess. You know what I'm saying? That's exactly what's happening. Right now, the good bacteria in our body are strong enough, and they're fighting the bad ones and saying, stay there. Okay? I'm not letting you go anywhere. Just stay there. At least, can you get rid of them? No. I think it's a little bit of this will be there in our bodies. They keep entering our bodies. When I'm breathing right now, I'm putting it in as well, because one of you will have a little bit of problem, and you're breathing in and out. So everybody's breathing in and out. So everyone is kind of accepting some bad bacteria as we go on. But is our body able to fight these foreign people? Yes, as long as you're strong. The moment you're weak, that's when your body will start going down. That's why when people get sick, because of one aspect, they start developing other complications. You're sick, and you go to hospital, and then you start getting other problems. This fails, that fails. Why everything is starting to fail is because there is a big fighting going on inside. Make sense? So burning energy. So energy can be used to do work, and energies can transfer from one form to the other form, and that's what we will see. Now first, let's focus our attention on the kinetic energy before we go to the potential energy. The kinetic energy part. And it is the energy due to motion. So let's say if you have an object. Suppose you have an object sitting on a surface, and you're applying a force F on the object, and the object drags through a displacement D. And if the object's mass is m, and let's say it starts from rest. Let's say it starts from rest. What will happen to this mass when you apply a force F? One word answer. Better word answer. More scientific answer.
Acceleration.
It will accelerate. Move is something that anybody can say. You ask a little kid, What will happen if I push this? It'll move. You can have a better answer saying it will accelerate. That's a scientific answer. Move is... Alright, so when I apply a force F on a mass M, especially if the question is directed that way, move is absolutely not the answer. Because I'm giving you two variables and I'm looking for the third variable. Force applied on a mass M, what will happen? It will accelerate. Clear? And when it accelerates, the speed is going to increase. It's going to change to a final speed. And during this process, it is moving through a displacement d. So let's look at work. How much is the work done? It is Fd, because the force and displacement are along the same directions. They're both in the same direction, so it's Fd. And what is F? Ma, right? So the work that you do is m times acceleration times d. Is it possible for you to connect this A, this, and this by an equation? What equation is that? Vf square is equal to Vi square plus 2AD. Right? D is, in this case, D is the displacement. We used to use X as a displacement. Now, so Vf, okay, now putting numbers into it, Vi square is 0 because I start from rest. And so we see that Vf square is equal to 2AD. So acceleration is Vf square over 2D. Plug this here. Plug that into this. And you have W is equal to m times Vf square over 2D times D. The D's cancel. The work that you do therefore is half m Vf square, which is the velocity that it gained from 0. And this is what we call as a kinetic energy. Well, the final need not be written at all. In general, you can just knock out the final because whatever velocity it is having at that stage, that is what we're going to use. So, in general, Ke is equal to half mv squared, where v is the velocity at that instant you're talking about. So how much kinetic energy will your car have if it is moving at a certain speed? So we can just plug things in directly. Your car has a mass of 4,000 kilograms, which is less than, wait, 2,000 kilograms. It's something like 4,400 pounds, which is possible, right? All right, 2,000 kilogram car moving at a speed of 70 miles per hour. What is the kinetic energy? So, so 70 miles per hour times 1.6 will give you in kilometers per hour. And then, so basically the 70 times 1.6 divided by 3.6 will be in meters per second. And then use that into the equation, half 2,000 times that speed square. How much is the answer? Is it taking so much time? How much? Give me scientific. 10 power? 6? 5? All right. So 9.68 times 10 to the power of 5 joules. That is the amount of energy your car has when your car is moving at that speed. It's a lot of energy. It can do so much damage to anybody or to yourself. It's a lot of energy, and the only 4 points of contact on the road are those tiny points of contact, and you sit pretty confidently sitting thinking that you are in full control of this energy. So you've got to be very responsible. Look at this energy. It's a lot of energy you are controlling. So anything can happen to that energy, can be dissipated in different forms, but if you don't want to dissipate it, then it's all in your control. Okay? Now, let's say it was already moving with an initial velocity. Suppose it is already moving with a velocity. And then you apply a force. It was already moving and you apply an extra force. It's like a football player is already running and somebody else comes and pushes him from the back with a force. What will happen to the football player? He'll go faster. He's going to gain kinetic energy. So something is already moving, and then the work is beginning to be applied. So the same story again, W is equal to force times displacement, which is equal to mass times A times D. And coming back to here, Vf square is equal to Vi square plus 2AD. And Vf square minus Vi square divided by 2D is going to be A. Substitute that over here, and you get mass times Vf square minus Vi square divided by 2D times D. And that becomes mVf square minus Vi square over 2, which is half mVf square minus half mVi square, which is kinetic energy final minus kinetic energy initial, which simply means change of kinetic energy. So the work done by the force gives what? Gives change of kinetic energy to the object. Because it already had some kinetic energy and you're boosting its kinetic energy a little more. So how much change in kinetic energy are you going to give it? That is so the work that you need to put in is this. Understand, just as work is a scalar quantity, energy itself is a scalar quantity. Power is a scalar quantity. Everything is scalar. Work, energy, power, everything has no direction. In one way it's good, right? Because if you have directional quantities, then it becomes difficult to tackle them. But if there's no direction, it's simply adding or subtracting, just like this. You're finding the difference of the two energies. That's fine. So work done is equal to change in the kinetic energy of the objects. Any questions here? An example would be an object was moving with a speed of 10 meters per second. An object of 5 kilograms was moving with 10 meters per second. And a force begins to act on it. And the object picks up a speed of 14 meters per second. The same object picks up a speed. It goes from 10 to 14 meters per second. And by the time it has moved 20 meters, what force was responsible for this change of kinetic energy? So what was the force that really made this difference? Okay. So what do you do in this case? What's the initial kinetic energy? What's the final kinetic energy? Find that out. That's a change in kinetic energy. And the change in kinetic energy is because of the work done. And the work obviously is because the force was acting on it. How much is the force?
240?
Force?
I probably screwed something up. I don't know.
12 newtons.
Well. Oh, newtons.
I'm asking for the force.
Oh, sorry.
What you found out was the energy difference.
Yeah.
Yeah. So the initial kinetic energy is something. The final kinetic energy is something else. The change in kinetic energy, if you work it out, it will come out 240 joules. And that is equal to the force times displacement. The force that is acting on it is F, displaced 20 meters, so therefore the force is equal to 12 newtons. So that extra force, or that is a net force that makes it go from here to there.
How did you find out 240 joules?
Take the energy difference. The final minus initial kinetic energy is half m Vf square minus Vi square, right? The difference between the two energies. Half of 5 times 14 square minus 10 square.
Squared, okay. I mean, I wouldn't have done that squared.
Oh yeah, square. That's a very common mistake, forgetting to square something. Now let's look at potential energy. Kinetic energy is half of v squared. So again, depending on the situation, depending on the problem, you got to find out what is happening. Friction always does negative work. Write it down somewhere. The air resistance, the frictional forces that is, against the body's motion, they're all going to be doing negative work. Like if I toss this marker up, watch. If I toss this marker up, what kind of energy am I giving to the marker? Kinetic. The moment I release it, I've given it kinetic energy. For doing that, I need to do work. That's why I'm moving it. See? I'm moving it, applying a force. Do you see it? But the moment I release it, I've given it the kinetic energy, and with which it's going up. And what kind of energy is supposed to gain? Potential energy. We are going to talk about that. Now, what is happening during the motion? Is there air resistance? Which way? So basically the air resistance is doing negative work, killing the energy. So the marker actually reaches a point below its actual capacity. You understand that? It should have gone from here to here, but air resistance makes it lose some energy, so it will only gain that much. Now, if it is coming down from here, it should come and land on my hands with a higher speed, but air resistance is killing the energy again. Which way is air resistance? Backward. So it is doing negative work. Air resistance always does negative work and therefore takes away the energy from the body. Make sense? Gravitational potential energy is gravitational potential energy. As we all know that any object has gravitational potential energy. We all have gravitational potential energy. This book right now has gravitational potential energy. But what happens is when you do some work on it, you can actually give it extra potential energy. Therefore, make it go up. Okay? Write it down. So, what is the force that is needed to be applied by me in order to just barely lift it?
The weight.
The weight. So the force I need to apply is just equal to the weight, the magnitude. Because the weight is acting downward, this is upward. Now, with this force, if I move it steadily, not necessarily accelerate it, just steadily up to here, I'm raising it by this displacement, which I'm calling it as h. So how much is work done? Force times displacement. What is the force that I applied? And what is the displacement? That's the equation for GPE. That's the equation for GPE, assuming that GPE here is 0. If GPE here is 0, then the GPE here is mgh. That is why instead of writing like this, we say change in GPE is equal to mg times change in height. So it's a change in height that we're more interested in and not really the height. The change in the height is what's more important than the real height. Yeah.
Do you measure from the bottom of the object?
You can measure from anywhere. It is just from the height, which is center to center, or bottom to bottom. Yeah, so work done is change in kinetic energy. Because you can see the consequence of applying a force is the object is moving from an initial velocity to a final velocity. So it is, well, can the initial velocity be 0? Yeah, it is possible. Is the initial velocity possibly negative? Yeah, it's possible. You can have any object moving anyway. So when you apply a force and displace an object, this is what the consequence is altogether. It had some energy, now it has a new energy. So the change in energy. Yeah, the change in energy, and of course we are focusing only on kinetic right now, not potential. Okay? Now, let's say, give an example here. Baseball, pitching the baseball. Okay? Now the baseball is pitched by a pitcher. And how he does it? He has to apply a force, right?
Yeah.
And displace the ball.
Yeah.
So he's not pitching it like from one point straight away goes off with a higher speed. No. What's happening?
Accelerates.
Yeah, he's kind of moving his hands backward and he's using all this distance. And he's applying what?
Force.
Force. He's applying force on this ball. So he's like throwing and he releases there. So let's take a baseball pitching example. What's the mass of baseball?
5 ounces.
Give roughly. Huh?
5 ounces.
I don't know. Ounces.
Like a fourth of a kilogram.
Okay, 0.4. Is it a pound?
So it's
No.
No.
0.25.
How many ounces a pound?
16.
Oh, it's far less than.
It's like 0.1.
Yeah, it's like 0.1 there.
Yeah.
Sort of. So 100 grams. Is that it? 100 grams?
Want me to look it up?
Yeah, you can look it up.
I'd say 0.1. It's probably close.
100 grams. 100 grams. Probably. Maybe 150 grams. I don't know. Yeah, because I know how much 100 grams will kind of weigh. I don't think the ball is. Probably 100 grams, yeah. It should be between 100 and 150 grams.
Yeah, 142 to 149
Okay.
grams.
So 150 grams. All right. So 150 grams, let's take it as 150. So the ball is 150 grams. The ball is 150 grams, which of course you know what to do with it immediately. Change it to kilograms, so 0.150 kilogram. And then the ball was at rest when his hand was like far behind him. And then, like, so tell me, what is the distance he's kind of moving his arms?
2 meters. It's like a meter that way or a meter
I
that
don't
way.
think it's, oh, maybe his movement also is there, right?
Well, because
2.5.
like your arm's like a meter
Yeah.
long, right?
Oh,
it's
no,
like
arm is not a meter.
Almost.
Almost?
Maybe
It says it.
Yeah, you know meter stick.
I don't know. I got long arms.
No, it may be 2 meters because you know why? Because he's not standing like this and doing
Yeah.
that.
Yeah.
So he's basically like having a kind of movement also, right?
Yeah.
So yeah, 2 meters can be an ideal thing. All right, let's say in 2 meters, the ball is being shot. But now let's find out the pitching speed. How fast is the pitching normally? How fast is
100 miles an
That's pretty fast.
100 miles an hour is a fast
90.
pitch.
as a fast pitch? Okay, let's
90.
take 100. Let's take 100.
Alright.
You're not going to pitch it, so therefore it's fine. 100 miles per hour. 100 miles per hour, and you know how to change this to meters per second. Because we need everything in kilograms, meters, and seconds. That's something that you should have learned already.
hour. 160 kilometers an hour.
160 kilometers an hour, correct. And then now what do you do to change it to meters per second?
Divide by 3.
Divide by 3.6, which is?
44.4.
All right. 44.4 meters per second is the speed with which it's going off. And this is 2 meters. Now let's turn back to the same equation we saw. So is the pitcher doing work?
Yes.
Yeah.
And what is it ending up?
44 meters per second.
The work that he did is ending up in giving the ball change in what's the kinetic energy start with?
0.
And here is the kinetic energy with which it's moving. So this is the kinetic energy with which it's moving. And you know the kinetic energy equation is half mv squared. Now when the initial kinetic energy is not there, the only thing over here is half m the final velocity squared. Is that clear? Now what is the work done by him? Is force times displacement. So now this force is questionable. Is he applying the same force throughout?
Probably not.
Probably not. And that's why I have to say this is the average force, not an average. So what is the average force that he has to apply? Calculate. Now you can calculate because you have everything there. What's the average force he has to put on the ball in order to get it going?
0.3.
So all you do is just substitute. So FD is equal, so F times D is equal to, okay, so F times 2 is equal to half times 0.150 times V squared, that is 44.4 squared. Don't forget to square that. A very common mistake from students is forgetting to square the velocity. So what is F, average?
73.9 meters.
Could be right. Yeah. Is that right?
Yes.
Okay, 73.9 Newton is the force that he's applying on an average. It may be, maybe he's applying the highest force in the beginning, and then as it is almost going out of his hands, he's probably not applying much force. When he's about to release, it's almost like 0, right? So 73.9 is the average force. Now see, how did you do this calculation? It's just by using the concept of work energy. And we are focusing on kinetic energy now. All right, now once pitched, the ball is going to suffer other changes of potential energy and all that stuff if it is going up. Now think of a football pitch. He is giving it change of kinetic energy. So he is giving it the kinetic energy, but as it moves like that, It's rising. Right? So therefore it is gaining some other form of energy, thereby it has to lose, so it slows down. So when he shoots a ball like that, it will slow down as it goes up, and then it will speed up as it comes down. Or think of throwing straight up. When the object is thrown straight up, it goes up and comes back. So when it's going up, it's losing its kinetic energy, but gaining potential energy. And then after that, it has to start losing its potential energy and gain back. Right? So understand the connections there. Any questions on this? The change in kinetic energy and the kinetic energy formula itself. Be careful. Don't use grams. Use kilograms. Don't use any other unit of speed. Use meters per second. Is that clear? Coming to potential energy, I told you there are different kinds of potential energies. GPE, then elastic potential energy, magnetic and other stuff, right? So we're not going into those areas right now. Magnetic, magnetic, electrical, electromagnetic, all those are there, energy forms. Light is an electromagnetic energy. Light is an electromagnetic energy. Sound is more of a mechanical energy because what's happening in sound is basically particles are made to vibrate. Yeah. So vibrations is what causes sound. So heat is also because of particles shaking. So you can cause heating effect. If I just hit the table, I'm shaking up the particles on the table, so which means automatically whatever energy I put on the table is now going as heat energy. So when you take a hammer and hammer a nail, the nail will be warm. Why? Because all the energy that you put into the hammer, GPE and all that stuff, abruptly comes to a halt. So where is it going? As heat. It has to come up as heat. It has to come up in different forms, sound, heat, okay? So, yeah, we're not going to talk about electric potential energy. We'll be doing it later on in the topic of electricity. Magnetic, not this year. Electromagnetic energies, yeah, we'll be talking about it when we talk about light. Okay? But again, that's not this year. All right, so coming to GPE, gravitational potential energy. What is potential? What is the gravitational potential energy? It is the energy. It is the energy that any object will be having if it is in the pull of gravity. If it's under the pull of gravity, it has gravitational potential energy. We have enormous amounts of gravitational potential energy right now, like 10 power 8, 10 power 9 joules. Plenty of energy. And one spot where there is no gravitational potential energy is the center of the Earth. Right? The center of the Earth, no potential energy because you don't go anywhere. If you're released there, you stay there. If you want to come out of the Earth, you have to climb up. Got it? You got to climb up. So, let's say you were there, and so you have zero potential energy to start with. Someone really hauled you up from there and put you here. So do you have energy now?
Yeah.
Yep. It's a big amount of energy. So think of it that way. Or think of it as, in fact, one other thing is gravitational potential energy is a negative quantity. We have a huge amount of energy, but it is actually a negative quantity. Again, why it is negative and all that can be seen later on. Right now, don't worry about whether it's negative or positive. Understand that every object on the surface of the Earth or anywhere around has to have gravitational potential energy. Right? So how much is the gravitational potential energy over here? I don't know. Well, can you find out? Yes, I can find out, but it requires big calculations using gravitation. Not too much, but I won't be able to do it right now because you have not done gravitational potential as a topic by itself. You learn some gravitation to help you with circular motion. Other than that, you've not done much gravitation. So if you do one more step into gravity. If you go in one more step, you should be able to figure out how much is the potential energy right now that I have. So for the time being, you don't have to really know that. Okay, so this is a mass M, which has some potential energy. Now, what is the minimum force I need to apply in order to lift it up? Minimum. mg. If I apply mg, I'm barely lifting it up. So which means if I keep applying mg, I may be able to make it move with a constant velocity, sort of, right? So my interest is not in speeding it up, but just to shift it. So a basic force that I need to apply is to just fight the gravitational force, which is basically mg. So this force will be just equal to mg. And if I lift this object and bring it to that height, did I do work?
Yes.
So if I'm lifting this object like that, it's going the same way. So positive work or negative work? Positive work. Because the force is upward that you're applying. And the height is also the same way. So therefore work done is equal to force times height. And what was the force? mg times height. That is the gravitational potential energy over here. Is that right?
Yeah.
As I said, okay. You can sit down.
Jacob, I see you're pulling your teeth so far.
All right, we're back.
One for one.
Don't question it.
Turn this way. Coming back to this. Do you know the gravitational potential energy of this book right now? No. I told you it's a big quantity, right? You have no idea about it. Do you know the potential energy here? Not really. But you knew how much you put in. So basically what you see over here is the change in gravitational potential energy. It is not the real. Make sense? And for that reason, work done is equal to the change in GPE. That's all you can tell. You cannot tell the real GPE. All you know for sure is how much work you put in. So you can only say, like for example, the book has some potential energy which I don't know. And suppose I put 100 joules into it. Do you know the GPE here? No. But you know how much it changed by? That's 100. So the change in GPE is mg times the change in the height. That is the important equation. So you may see in some textbooks, they say potential energy, mgh. That is not right. Potential energy is not mgh. The change in potential energy is mg times the change in the height. Make sense? Yeah.
How do you know the change in the height?
Oh, like this. You know how much it is.
Okay.
Yeah.
Height. How much you take it, that is up to you. So if I'm actually taking the book from here to down there,
Negative height.
it's negative because I'm pulling it up and it is moving down. Make sense? So it's basically a negative GPE. It's losing it. Yeah.
How do you get the units to line up for that?
The same units. All units are the same, exactly. Didn't I go through the units part of it?
I don't think so.
Okay. You know, work done is force times displacement.
Yes.
Oh, that's very strange. Okay. What is force? Newtons. And what is displacement? So that is a unit of energy. That is a unit of energy. But instead of writing like that, we have a shortcut unit, which is joule. So a joule is nothing but a Newton meter. A joule is just a Newton meter. What does it mean? It means if I apply 1 Newton and push an object through 1 meter, I have done 1 joule of work. Is that clear? If I apply 1 Newton on an object and I push it for 1 meter, I am doing 1 joule of work. That is a unit of, this is the SI unit of energy. This is also the SI unit of energy, but they are not in basic terms. Yeah.
Is joule spelled like a gem or?
Oh, not joule. No. All right, now here, if you want to break this energy unit into basic terms, it's very easy. This is already in basic, and you know what is Newton, right?
Yeah.
What is Newton? Mass times? Mass times acceleration. Kilogram times meters per second squared. And then that meter along with it. So what is it? Kilogram meter squared second power minus 2. That is joule. So this is the basic unit of energy. This is a derived unit of energy. Make sense? This is also a derived unit of energy. But when you talk about energy, we don't use Newton meter commonly. We say this. But is there anything wrong in saying Newton meter? Nothing's wrong. When you're mentioning about energy, we always use joule. Okay? And only when you're asked, give me the unit of joule in basic terms, then you put this. This is only necessary then. We don't normally use this for regular energy units. Yep. Okay. All right. So understand that GPE, change of GPE is mg times the change of height, because we don't really know how much is the actual GPE. It's like this. Imagine we are walking together and we go to the railway, the gate, and a train is already like halted over there. You know, one of these trains. It's like standing there, and you're probably right in the middle of this. And then I'm asking you one question. What is the mass of the train? What could be your best answer there? What's the mass of the train? A lot. Yeah, I don't know. Seriously, you don't know. You don't even see the ends of the train, and you don't know what is inside the train, and you have no clue at all. But is there a mass?
8.
Is there a mass?
Yes.
Definitely there's a mass, but you have no clue about it. Right? And after you said, I don't know anything about the mass, then I'm asking you, all right, step onto the train, because it's not moving, you can always step on it. So you step on the train temporarily, and then I ask you the same question again. What do you know about the mass of the train now?
Plus your weight. And plus your weight.
Yeah. So you know that the mass changed by your mass. So if you weigh 80 kilograms, when you step on it, you confidently can say the mass of the train changed by 80 kilograms. That's exactly what you're saying here. Make sense?
Yeah.
You don't know the real potential energy of this object. And you don't know the potential energy over here also. But you know what changed. So we are focusing only on our changes. In some questions, they will say, take this ground level as zero potential. In that case, you're going to refer to this as a zero and then answer the other questions. Right? So if they tell you, take the tabletop as zero potential energy. Now tell me, what is the energy of this? Then you say, mgh. What is the energy of the same book when it's on the floor? Minus mgh.
So we pretend the table's the center of the earth.
Exactly. So, yeah, you pretend that this is the reference level and that's the zero level. So very commonly you'll see such things. With reference to the tabletop, what is the potential energy of this? So basically they're telling you, all right, imagine this is your reference. Now what is this? So there are situations where you need to just look into the problem that way. So that's basically potential energy. Any questions about potential energy? Simple formula,
Yeah.
but you need to apply them when the time comes. The other one is elastic potential energy. let's talk a little bit about the elastic potential energy before we go ahead. And you will be doing labs and all that about springs. Okay, there are many labs kind of waiting for you. And you cannot do the labs before you learn the topic. That is the other issue. So normally this is how it goes. We do some and we are waiting for the topics to be completed so that you can actually get into the labs. Make sense? If I gave you a spring lab before even doing anything about springs, it will not make any sense. So once you learn something about it, then if you do a corresponding lab, it will strengthen what you're learning.
Are we gonna have any more labs?
Oh,
for
plenty
this
more.
semester?
This semester? Time is... Again, the
3
topics,
classes left.
as I said again, it's all depending on the topics. So since the topics are, we could squeeze in that spring lab, possibly. But there are other labs also that needs to be done. Plenty more. So you will do many labs. Next semester will be like, I can be faster with the topic, hopefully. And we'll get more time to do the labs. So let's talk about the springs itself. A spring that's basically an unstretched spring. Okay, this is an unstretched spring. Now, what is one of the properties of the spring is like you apply a force, then it should start stretching. Right? So when you apply a force, it will start stretching. The same spring, when you apply the force, it started stretching. And so you can see how much it stretches by is this. It is stretching by that. Now, you can call it Y, you can call it X, depends on the orientation, but I just keep it as X. Some books use E, just to say this is extension. Okay? So whatever format of the equation you see, you should be able to understand what these things are. If it is X, then understand its extension. If it is delta X, understand that's also the same thing as extension. If it is E, understand that way. If it's Y, understand it the same way. So basically I'm trying to say extension. And what we know is the more the force you apply, the more the extension. Is that right for a spring?
Yeah.
So the more you apply a force, the more it's going to stretch. So this is going to be a graphical format of your force extension. When you applied no force, no extension. When you applied some force, it extends. So that is going to be a straight line variation. So F is proportional directly to X. And of course, this is not true always within proportional limits. Within proportional limits. And elastic limits. So now coming back again, this spring, it could be flexible, but it is elastic. So when is this true? It is true only when you are within proportional limits, which means straight line limits, and elastic limits. Don't want to break it. If you cross those limits, it may show some bending. See there. Now look at this.
There's always one.
This is supposed to be a good slinky, and you can see that someone has wrongly used it. Can you see that gap? Permanently damaged over there. That's because someone actually pulled it, crossed the. Once you cross the limits, then it can permanently also deform. Okay, because this is not purely, it's not purely steel. It's not purely steel. It has got some iron in it, and therefore, can I bend it? Yes, possibly. I can bend it. But a proper steel spring is not supposed to bend. Your shocks in the car, they're not supposed to be like permanently damaged. Not supposed to be. But again, as they are not 100% high carbon steel and all that, there will always be a kind of weakening effect as time goes on. Okay, so F is proportional to X. That's one thing you should understand. Now, this is a graph for one spring. Will all the springs exactly show the same kind of graph?
No.
No. You can have a slinky which extends so quickly with the smallest force, which means this will be for a slinky. See, the smallest force stretches it a lot. Now, some springs require a stronger force. What about your car springs?
Very strong.
You need a lot of force to stretch it even by a. So they will go like this. So you can see that yes, F is proportional to X, but there is some constant of proportionality here, which is what we call as the force constant of the material, the spring. So F is equal to Kx, where K is called the force constant of spring. Now, if you don't know what material it is, if it is not a spring, just say force constant of the material, whatever. F is equal to Kx. Is that clear? Good. Now, normally, when you have force and displacement, and if the force is steady for a certain displacement, how much is work done? FD, right?
Yeah.
You did it already. So if the force is steady and the displacement is produced, FD is the work done, correct?
Yeah.
But if the force is not steady, so what is FD? The area under this graph.
Yeah.
The area under this graph is FD, the work done. So what if the force is not steady? If the force is like changing like that, and you moved it, the force is not steady, still the area is work done. Make sense?
Is it still FD?
It is not FD, but yes, F of F. You take the F every moment, and then basically you're going to take multiple rectangles. Can you see that? You take multiple rectangles because the force is changing all the time. So then overall, the work done is the area under the graph.
So it's the average force times the displacement.
Exactly. Now coming to a spring, you know it's a straight line. And because it's a straight line, the work done by this force is going to be the area of the triangle. And you know that the highest point is F here, and this is X here. So what's the area of the triangle?
1/2 of X.
Work done is equal to area, which is half times base times X, right? Half times base times height.
Yeah.
All right. Now what is F though? What is F? F is Kx, right? Put that Kx in here. So you'll see the work done is equal to half Kx squared, which is the elastic potential energy. That is the elastic potential energy. So if you have a spring that is stretched by that much, then how much energy does it store? Half Kx squared. So this is basically the equation that I am coming to. Okay, that is the equation for elastic potential energy. Now that you have gone through all the different potential energies that we need, we are going straight into conservation of energy. Next class.